where I think we're saying to these boys here, if you know what you're doing, so long as you don't make those like silly mistakes where you go, oh, I can't believe I used the wrong molar mass. It's very repetitive in a way, which is good. One of the downsides though is you have to do a lot of small little calculations.
Mr. Petluck, can you please call 100?
Like for example, you need to be able to balance an equation, right? Well, if you struggle with writing an equation, then you're going to make a mistake, right? Or you have to find molar masses. Well, again, if you like, for example, call water H3O rather than H2O, you're going to screw up, right? So you got to watch like all those little mistakes. If you can eliminate those little mistakes, you'll do quite well in this unit. Okay, here's today's topic. I want to present the analogy of cooking again. I like analogies. You guys probably know this by now. So imagine that my wife decided to make some cookies. And in order to make cookies, she did what you guys just did, where she went and found a recipe, which in your example is you find a balanced equation. And she goes to the kitchen and gets the right amounts of flour and sugar. And maybe I've talked with you about the idea of, there's certain spectator ions that you don't really need to have as part of the equation. Now, if you wanted to, you can maybe substitute flour or substitute butter for margarine. That would still work. Okay. Well, going forward, let's say my wife cooks those cookies, and there's supposed to be a dozen cookies sitting on the pan in the oven. And she takes the pan out of the oven and sets it on the counter to cool, and there's supposed to be 12 cookies there because we calculated those, right? And she comes back a little while later, and there's only 11 cookies there. What happened? Yeah, I still won. It just looks so good, right? Well, we have a similar problem in chemistry where you expect to make 12 cookies, and for some reason only 11 show up. And the concept is called a percent yield, where sometimes you don't get as much as you were expecting. And there's a lot of different reasons for that. Like in the kitchen analogy, it's because I stole a cookie, obviously, right? In chemistry, there are a lot of different reasons why, and sometimes it's a bit of a mystery. But if you're expecting to get 100, sometimes you might only get 99.4. Does that make sense? And so today's concept is very simple. To find a percent yield, you basically take what you actually got, divide by what in theory you were hoping to get, and times by 100. So in my wife's cookie example, if she made 12 cookies, that would be theoretically there should be 12 cookies on the counter. But I ate one, so there's only 11 there. So to find the percent yield, it would be 11 divided by 12 times 100. That makes sense? When we do labs, we're hoping to get as close to 100% as possible. Sometimes you only get 80% because of... well, actually, I've got a slide later that talks about why. Let's do some examples, because this is pretty straightforward, actually. So you're probably going to get a question where it starts off very similar to what we just did, where I'm going to give you a problem. First thing you need is the recipe. So it says copper is produced. So that means copper is being produced. And here it says that you've got some aluminum and some copper sulfate. Thank you. As I read this is kind of like the stem of the equation here. I just kind of wrote out what I saw. It said copper is produced when aluminum reacts with copper 2 sulfate. This isn't enough on its own for the whole recipe, though, is it? What am I missing? What kind of reaction would this be? If you have aluminum and copper sulfate react with each other. Yeah, it's single replacement. So it means I'm missing a product. What's the other product going to be? Good. We need to make sure we get those charges right, though. Because aluminum's +3 and SO4 is -2. If you mess up on even that little detail, the whole question is shot. You know what I mean? So you need to put a 2 here and a 3 here. Sorry that mine's kind of messy, but you need this plus this reacts to make these two guys right here. One of the things that I've chatted with a few of you guys about is the idea that if this is aqueous right here and this is aqueous right here, what's the spectator ion that could be canceled out? Good, SO4, yeah. This SO4 right here and this SO4, it could have been canceled. The analogy I would give then is, let's say I want to make copper solid, and I don't have copper sulfate, but I have copper nitrate. Could copper nitrate be a reasonable substitute? Sure. Yeah, I think it would work. If I wanted to make copper, could I use barium sulfate and have that work though? I'd say no, it has to at least have the copper as the starting piece, but the second half of it could be maybe something different. That's like the butter versus margarine analogy. You could probably get away with making it with margarine if you don't have butter. Does that work? So ultimately though, that's not really relevant in solving the question. We need to balance the thing. So to balance it, you're going to need a 3, and a 2. Does that make sense so far? Okay. Now to answer my question, what was the actual yield? We actually have that written in the question. Yield kind of refers to like the thing that you make. The answer for the actual yield is 678 grams of copper. This is how much actually was made. Or if you like my cookie analogy, my wife actually made 11 cookies. Right? When she goes and looks at how much cookies she made, there's only 11 there. That makes sense? What I want to figure out is, theoretically, how many should there have been there? Because in theory, she actually made a dozen, I stole one. Okay. So to find the theoretical yield, I'm going to use the other number. And I'm going to start with that. So I'm going to start with the 392 grams of aluminum. And we're going to do what you guys just spent the morning doing. So what's the next step then? Do we want grams? Okay, we don't want grams, so to get rid of grams, we use a mole-gram ratio for aluminum. Is it 2698? Better not get that wrong. Good, okay. Next step after that, we were going to take aluminum, so we're going to take eggs and flour, and we were going to make some copper, or cookies in this example. And the ratio is 3/2. And last step is copper's molar mass, 5585. Boy, I feel rusty on this. No, 6355. Cancel, cancel, cancel. Basically, at this point, you just need to know how to use a calculator. I got 13.9 myself. Anybody else get that? Yeah. Okay. This number should have been bigger than 678. It has to be. Because 678 is how many cookies were left after I stole a few. Does that make sense? So in this example here, my wife actually made almost 14 cookies. But by the time she came back to the kitchen, me and Kinsey Ann accidentally ate 7. Accidentally. Does that make sense? The same thing happens in chemistry due to various different reasons. So last step to find the percent yield, just divide the two numbers. So take 678 grams. And what I would recommend doing though is, even though I wrote this as 13.9, my calculator actually spit out 13.8500. Like, try to use the actual number that you previously had there. It makes the answer more makes it more accurate. Precise would be more decimal places. Accurate means more correct. The more I round, the less correct my answer is. So try not to round until we're done. So 678 divided by my answer times 100. Now I'll round. I got 48.9529. So with 3 sig digs, it's going to make it 49.0%. Do you guys know the word efficiency? I'm doing it with my grade 10s right now in their science class. I mean, some reactions are just not very efficient. Ideally, everything you start with should react. But sometimes that doesn't work that way. We've actually used this term before in this class. We talked about strong versus weak acids. You guys remember these terms before? Originally, I told you strong and weak were based on how something conducts, but that was kind of a partial truth. Strong and weak were based on if you have A and B, and 100% of it actually reacts to turn into C and D that makes it strong. Whereas like weak meant that like this was like 50% or less. Does that make sense? All reactions have like a completeness percentage in terms of like, ideally everything reacts. But for whatever reason, sometimes maybe only half of it reacts or 3/4 of it reacts. The job of a scientist then is to try to find a way to make it so that more products are made, because if you can up the efficiency of your reaction, then that's a better thing. Does that make sense? Any questions on that? No. So here's some reasons why. Put a star next to this because I think this comes up on one of your labs. When I ask you why are reactions not 100%, here are some of the most common reasons why. So, the first one is measurement uncertainties. Whenever we measure things on a scale, we have to round at some point. Like for example, if I go to one of the scales, it might read 100.0, but on another scale, it's actually 100.015379. If you get what I'm saying here, like at some point, numbers are being rounded. And often it's small, but I mean, enough rounding accumulations and it's going to cause your values to be slightly out. So, often chemicals we use are not perfectly pure. Like for example, if you had a jar of potassium nitrate, we used that before, and you were looking at all these crystals inside the jar, ideally there would only be potassium nitrate crystals inside there. But in theory, there could be like a fleck, and this guy right here could somehow be like a calcium carbonate that somehow got inside there. Does that make sense? And if it wasn't 100% pure chemical, then it might be slightly out. The chemical grade that I usually buy is about 99% pure, but like there's going to be extra little grains of stuff in there. Like we're not a clean room where I can guarantee that nothing else gets inside these chemicals. Does that make sense? Like even as you breathe on them, you might be getting a little bit of dust or some, like maybe a hair particle falls onto the scale. I don't know. This one right here is what we're going to do eventually in a lab. Sometimes when you need to separate materials, we have to do something called washing a precipitate. It's really a fancy word for filtering. Let's filter. So imagine that like as part of your reaction, it produces something aqueous and something solid. How do you separate the aqueous thing from the solid thing? Well, filter is a great way of doing that. The only downside is what happens when you put stuff through the filter? What if like some of it actually goes through the filter and it wasn't supposed to? Does that make sense? And so a filter is not perfect. You know, something is going to make it through that's not expected to. So there's another reason. And then this kind of is fairly general. Any estimations you have? I talked with a couple of groups about how in one of those examples there, it could be copper 2+ or copper 1+. And we don't actually know which one it's going to make. We guessed that it was going to be the top copper 2+ because that was the first one listed. But what if there was some copper 1+ in there as well? So long story short, if you like my analogy of cookies, if someone makes 12 cookies, I guarantee that there won't be 12 cookies left when you're done. It might be 11.5, right? But like there should typically in a real life scenario be less than what you start with. That's just a reality of doing practical hands-on chem. Sound good? Cool. All right. You guys have about half an hour. I might recommend with today the two most likely things you should do: print off tomorrow's lab and get a look at some of the post-lab questions. And second thing, you could start on your assignment. There's only 8 questions, but you can probably do the first couple. Yeah, for sure. Yeah, for free. Grab it there. Okay. Let me know if you guys have questions.